everybody. Welcome to another episode of our DE 24/7 podcast. This is Kenneth Wong, Senior Editor for DE 24/7. Recently, NVIDIA announced a series of partnership. Specifically, we want to focus on their partnership with Cadence, Dassault Systems, Siemens, and Synopsys, because these are household names in design and simulation sector. They affect the way you do engineering job. So today we are speaking to Tim Costa, General Manager and VP of Industrial and Computational Engineering at NVIDIA, to better understand the nature of these partnerships. So Tim, welcome. The first thing I'd like to ask you is these partnerships with the four vendors that we have talked about, and specifically, they are probably inventing things like GPU acceleration, Omniverse integration, CUDA-X libraries, and things like that. Are they pretty much doing it the same way, or do they each take a different approach?
It's a great question, and also thanks for having me on here. We're in the midst of a revolution in design and engineering. That revolution is driven by the same AI technologies that are creating a revolution in so many different industries, but the impact is no less profound on the ability to design and engineer the things that matter to us most, things like automobiles and airplanes and industrial equipment and semiconductors. And that last bit is kind of particularly interesting because there's this virtuous cycle of innovation between AI technologies creating better semiconductors, which can then create more capable AI. So all four of these partners of ours are seeing that same revolution taking place, and of course, it's an opportunity for them to serve their customers better and help their customers to be able to create more advanced technologies and be more successful in market with this innovative new technology. Now, they all have, different areas where they differentiate from one another, and I'm certainly not here to speak on their behalf in that way. But what you'll see across them all is an enthusiasm for integrating accelerated computing. The whole effort to bring this revolution to bear on this market and industry starts with the acceleration of the core workloads, making fluid dynamic simulations faster and crash and structural simulations faster and more capable. Thermals, acoustics, lithography, TCAD, all kinds of workloads that are critical in this industry, making them much faster. That's kind of where we started. The second pillar then is engineering with AI. And we mean that in two different ways. We mean that in terms of integrating AI physics to create a speed of simulation, a capability which isn't just improving TCO, but really transforming what's possible into a world where you can do real-time simulation that merges design and engineering. And then the other part of engineering with AI is agentic AI. If we take the kind of workflow of engineering, it starts with having an idea, it goes into CAD, you do geometry and meshing. From there, you've got a big simulation amount of work to do. And then you post-process and you build reports and you convince your management you've got the right thing to build, and then eventually you go into manufacturing. All the way across this space, if we take a look at each one, there's an opportunity for AI to really compress the life cycle and improve the time to market and the ability of these companies to build more advanced kind of products. You have the AI physics for the simulation part, but then with the rest of those steps, you have agents coming in who are going to be able to just dramatically compress that timeline. So engineering with AI is a huge opportunity for these companies across this space. And then finally, our kind of third pillar that we work with both these ISVs and the rest of the industry is connecting the real and digital worlds through real-time digital twins. Now, these three kind of pillars, they may feel separate, but in fact, they're really fundamentally linked to one another. You can't do a real-time digital twin if your physics simulation takes 3 days, right? That can't be real time. The interactivity is kind of pointless at that kind of speed. You need to get to the point where your fluids problems, your structures problems, your acoustics, your thermals, all these different workloads are running in real time. And so design and engineering can cohabitate and work on the product while getting instantaneous feedback. To do that, you have to have a lot of data that you can't download from the internet. There's no way you can download the internet and train a fluid dynamics model. And what that means is you have to do a tremendous amount of first principled simulation, of core workload simulation for these different application areas to generate synthetic data and train these AI physics models. So when we walk through these, these three pillars in one direction, as we look back, it's actually one relies upon the other, and it's all very interconnected. So you'll see from Cadence, Dassault, Siemens, Synopsys, all of them engaged across all of these different areas, with, of course, their own differentiations, but all because they see the same fantastic opportunity to participate in and accelerate the AI revolution for design and engineering.
Many of these vendors, well, all of these vendors usually like to talk about the robustness of their physics solvers. And by that, they mean fluid physics, uh, structural dynamics, thermal, electrical, things like that. And when you were talking about Omniverse, Omniverse also seems to have its own physics framework where walls behave the way walls should behave, water should behave the way water should behave, and things like that. Are they the same type of physics? Do they work with each other? Do they complement each other? How should, what can you tell me about the interaction between these?
Yeah, absolutely. I think that for that question, it's important to first take a step back and think about, what kind of company is NVIDIA in this space? NVIDIA is really a platform technology company. So when we work to accelerate the companies that do work in CAE and EDA and other parts of design and engineering, our contribution are core libraries, platform technologies that can integrate into our partners' solutions so that they can take to market with the end customers. And that's been that's certainly true for our CUDA-X libraries that really are focused on first principled solver acceleration. Libraries like cuDSS, cuEST, the list goes on and on. There's some hundreds and hundreds of these libraries. It's also true for Omniverse, which is really a collection of libraries and APIs to help these partners of ours provide technologies to build digital twins and connect the real and physical world for these end customers in design and engineering. So I don't think that we don't think about it as being a different type of solver or the same type of solver, but rather we're really one click below those physics solvers across our portfolio, and really just providing those core library APIs to accelerate workloads and to connect the real and physical worlds through digital twins.
In a GTC keynote, NVIDIA CEO Jensen Huang introduced the Rubin Vera DSX reference system. And he also paid tribute to these partners for their contribution to the system. Some of them seems to have helped the simulation. Some of them seems to have helped the data center building itself. What can you tell me about their contributions?
Yeah, so I think there's two important points to the answer here. One thing is that you mentioned it as a reference architecture. One thing that we really embrace in this space is the idea that we want to publish blueprints for how our technology can be used in the design and engineering space, not as a solution for industry to adopt directly and take into their processes. A good example of this is the OV-RTDT, which is a real-time digital twin that we launched at Supercomputing 2024, if I'm not mistaken. I got my times right. And this provided the ability to do real-time fluid dynamic simulation around an automobile, and you could change pieces of the car and get the real-time solution, and it's nicely visualized, of course. This was done with a number of different partners, and not only was it built in collaboration with partners, but it exists so that it's a reference for those for other partners to then integrate these technologies and provide the capability to their end customers. And that's true as well for the reference architecture of DSX. And so what you'll see is that different partners in the DSX effort will have contributed in terms of the design of what is the interface between the different components of these complex workflows. Then when it's demonstrated, actually using their technologies in that workflow in order to create the demonstration. I think when we did the OVRTDT, one of the companies that was featured was Luminary Cloud, and Luminary Cloud participated in. We actually used their solver to generate data to train the model, and so their solver was directly integrated into the OVRTDT at launch. But of course, so many other partners since then have adopted that blueprint as a guiding light towards building their solutions and taking it to market. And you can expect the same from DSX.
Our readers, of course, very familiar with these partners that we just talked about because their bread and butter is these CAD and simulation softwares. What else do you think is important for them to know about these partnerships?
Sure. I think that the most important thing for everyone to have in their minds is I mentioned it a little bit in my first answer to your first question. We are really in the midst of, but I would argue even at the beginning of an AI revolution in design and engineering. I've been in this industry. I've been in the scientific computing industry for many years, and there really about a year and a half ago there came a moment when there was a stark change in the way that the enterprises in this industry reacted to and responded to discussions about AI for physics workloads, for engineering workloads. Before that moment, it was prove it to me. There a lot of reticence and discomfort and wanting to, and not sure that we should really be putting AI into some simulation of these workloads. But after that moment, the tone really changed, and it was around supercomputing 24, and at least for me personally, my experience with it. And the response became, show me how. How do we do this? So there's this tremendous hunger in the design and engineering space to adopt AI, both agentic AI, AI physics, physical AI, as we move towards the manufacturing side of these of the design and engineering industries, because the opportunities are clear, the capabilities are transformative. And the equipment and products that these companies are trying to build are so complex that they're looking for technology to help us move forwards, and it will touch our lives every day as it starts to impact the design and engineering space. So a really exciting time, and I think there's lots to watch here as different capabilities are developed and then implemented and deployed. At big companies that everyone interacts with every day as they get in their cars and their airplanes and use their computers and so many different other parts of their lives.
Tim, thank you very much for your time. I appreciate it.
Sure. Thank you very much for having me.
All right, audience, that's all for this episode. Until next time, I'm Kenneth Wong, Senior Editor for DE 24/7, and we are out.